I hope you guys are doing all right. Today is the 14th of April, and we're going to talk about acids and bases today. Now, we got a good chunk of material to cover today, and we're going to be all right working through it. If at any point there's something that you're like, whoa, 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 stop the press, let me know. I've got my chat window open, and so I can see what you guys are saying, and we'll go from there. Now, I'm recording. Got the PowerPoint up. I'm ready to go. I hope you guys are as well. I'm recording. I throw it on YouTube and Canvas like always. And so we'll be good to go. A week from today, we will be reviewing for exam number 3. I'm going to give you a practice exam, and that should be up no later than Wednesday. Um, if you got questions about anything, from basically either from exam 2 or this most recent stuff, let me know. I've got office hours at 12:30 today, so you can join that link and I'll answer any questions you got. Other than that, though, let's get cracking. So, acids and bases and pH. I presume all of these things are terms that you've heard before. Um, when I was a kid, I think the first time I remember hearing the term acid, I was thinking about, or I was told about acid rain. And then the next time I remember hearing about it was in the context of the psychedelic drug acid, which I think acid's a psychedelic. I'm not exactly sure. And then learning about what's his name, Timothy Leary. He was a professor. I think he was at Berkeley. Um, it was either Berkeley or MIT, and he was yeah, he experimented a lot with that sort of acid. That's a different acid than what we're going to talk about, though, if I remember correctly, the compound or the drug acid is actually, by our definition, acidic. So that works out fairly well there. Um, at any rate, acids, bases, and pHs, proceed. Of course, I say proceed, hit the button, and it doesn't do anything because I had the wrong thing selected. Now proceed. We're talking about acids and bases, chapter number 7. Wednesday, we're going to do chapter number 8, and done. So, what comes to mind when you hear the words acids and bases? I've shared mine. I said, well, acid rain and then the drug. When you hear the word acid, what comes to mind? Add it to the chat. The Joker and Harley Quinn? 14 hours of vivid imagery. I think I've looked up that YouTube video. It's just ambient noise and then um okay, citrus. Yep. Acid reflux. Totally. A good okay. 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 What about bass? Oh, we got an alien emoji. What about bass? When you hear bass, what comes to mind? What comes to mind is okay. Bottom. Okay. Okay. Whenever I hear bass, the first thing that comes to mind was the homecoming carnival when I was in ninth grade, and somebody coming in a Honda Civic, and they had like 12-inch subwoofers in the back of their car, and they played Brass Monkey by the Beastie Boys really loud, and you could see the subwoofers shaking, and that was, I remember thinking, man, maybe that person's cool. And then a little while later, I was like, I don't think that person's cool. But anyway, that's what I think of BASS. And then, of course, my mind goes on to fishing, but that's not where it goes. We're talking about acids and bases as kind of complementary compounds to one another. Now, acids and bases are something that's very common around your household. We've got Drano, which is sodium hydroxide, which is a base. Um, then we've got ascorbic acid or vitamin C, acetic acid, which is your vinegar, NH3, which is ammonia, and HCl, which is an acid that people use. Well, it's hydrochloric acid. Um, and this is really just, if you look at this label, you'll see that it says muriatic acid. And that is not the same thing as HCl. In the chemical context, oh, thank you very Sam, thank you very much. Yes, totally. Yeah, that's where I actually paused and stopped watching Breaking Bad because I was like, that's pretty intense. HCl is hydrochloric acid. You've maybe heard about hydrochloric acid as being the primary acid that's in your gut that helps you dissolve or helps you, well, digest things. But HCl and muriatic acid, those are also acids that people use in their pools or in their hot tubs to help maintain a pH that's, well, not going to allow bacteria to grow and that's, healthy for or not harmful for you to get into. Now, an important thing that you guys need to know about acids and bases in a chemical context is just a second. Okay. Um, is some of the properties. First and foremost, I think that it's pretty common for someone to hear of like, oh, I got an acid burn, but it's maybe not so common to hear about a base burn. Well, let me tell you that a base burn is something that can absolutely happen. And the a base burn is it's maybe a little bit surprising. And the reason for that is if you have a base that ends up on your hand or on your skin and it sits there for a while. Well, the first thing that you're going to notice is that it kind of has a slippery texture. Like if you get it in your fingers, you'll be like, that's a slightly weird sensation, and your fingers will kind of feel slippery. But if it stays there for a little while, then your fingers that were once slippery are a little bit red because, well, your skin has been burnt. And bases taste bitter. Acids, by contrast, they taste sour. And one of the things that they do that's a little bit more dramatic and exciting than a base is that they dissolve metals, specifically active metals. And this is something that we're going to get a little bit more into on Wednesday in terms of what constitutes an active metal. But that's what they're going to do. In addition to that, acids will turn blue litmus paper red. They will react with a base to form a water and a salt. By comparison, if you use red litmus paper, well, a base will turn that blue. So this word, litmus, that's kind of it's a good word to describe something that just sort of checks. It's a type of paper that gives you information about a solution, or it's a litmus test is maybe something that you've heard. And that kind of originates, to my knowledge, from acids and bases. There are two different types of litmus paper. Blue litmus paper is really good for checking if you have an acid. Red litmus paper is really good for checking if you have a base. Um, Go ahead and add to the chat. What color do you think red litmus paper will be in an acid? Add R for red or B for blue. You take an acid in red paper. You got to vote for red. If you get that red litmus paper, that checks if you have an acid. If you dip an at a or sorry, it checks if you have a base. If you take red litmus paper and dip it into an acid, it doesn't change at all. Red litmus paper is great for telling you if you have a base. So if you dip that into acid, well, an acid is not a base, so red litmus paper says nothing. If you get red litmus paper and you dip it into a base, that's when it changes. So when you think about red and blue litmus paper, think about them as telling you um, the opposite of what the color corresponds to. So to illustrate that, this right here, this is blue litmus paper. And this looks, it seems, when you look at it initially, it seems like, oh, we're looking at the same thing dipped in different, it's just been flipped over or something like that. No. On the left-hand side, we've got blue litmus paper. On the right-hand side, we've got a paper that looks very similar, but this is red litmus paper. Your blue litmus paper, when it turns red, well, that says you've got an acid. Your red litmus paper, when it turns blue, that's a base or a basic solution. So, whenever it changes, that's telling you something. Now, I said a little bit ago that an acid is going to dissolve an active metal. Now, what you can see here is a strip of magnesium that's been dropped into a solution of hydrochloric acid. And what's going to happen here is I'm going to write this reaction out. Magnesium, whenever you see something like solid magnesium, that's also known as elemental magnesium, so Mg, plus HCl. That is a metal. That's a metal reacting with a strong acid, and that's going to produce, well, MgCl2 and H2. That is going to produce hydrogen gas. So a reaction between hydrochloric acid and magnesium will produce magnesium chloride and hydrogen gas. Now, my reaction there is not balanced, but I think we can balance it pretty quickly. Does anyone have any proposals on how I could balance this? I give you a little bit of a hint by rewriting where I put my plus. How about I put a 2 coefficient right out in front of the... Perfect. Great job, Emma. Thank you. 2 HCl. Balanced. Done. Okay, so this hydrogen gas is going to bubble up. It's going to evolve through that solution. It's going to be released. Now, there are two major theories on acids and bases. The older theory is known as the Arrhenius, or Arrhenius acids and Arrhenius bases. And they're a little bit different. For instance, an Arrhenius acid produces hydrogen ions in water. An Arrhenius base produces hydroxide ions. But it has some limitations. It doesn't, it basically says an acid or a base has this or this. Now, the definition that we're going to use and that I want you guys to know is what's known as the Bronsted-Lowry definition. So, the Bronsted-Lowry definition basically says an acid is a proton donor and a base is a proton acceptor. And a fair question there is to say, well, how do I define or how do I identify one or the other? And I think a good way to look at it is to use some examples. So let me ask you this first and foremost. Or actually, H2O. This is not a trick question. Um, Add a Y or an N to the chat as a response. Does H2O have a positive or a negative charge? Do you see, did I write one there is my other question. It's neutral. Haley, perfect. We're going to get there, but you're absolutely right. Water is neutral. Okay. It has no charge. So neutral is a great word that I want you guys to be comfortable with. When it comes to acids and bases, and we're going to look at a graph of this in just a moment. When we talk about acids and bases, and when we describe solutions, we describe them as acidic or at kind of the opposite end of the spectrum, basic. In the middle, it is neutral. So an acid can donate a proton and a base can accept a proton. Now, if we look at some reactions, Lisa, yes. That's the next slide that we're going to take a look at. You're absolutely right. Thinking about the pH scale. Fantastic. Those are our boundaries. Acidic, basic, neutral in the middle. So I'm happy that you're thinking about that because that's where we're going. Now, what I want to do is I want you to look at these two molecules right here. We've got HCl on the left. I've labeled that A. And then we've got water on the right that I've labeled B. If you get HCl and you add it to water, this is a good visual of what happens. HCl, that two atom compound, reacts with water, and the result is a negatively charged chloride ion and a positively charged, this is going to kind of blow your mind, but this is referred to as a hydronium ion. Okay. So the way that I think is really effective to think about this, however, is not to get thrown off by hydronium ion and think about, well, what happened to the water? But instead, look at your chlorine, that Cl. Now, what I want you guys to do is tell me A or B using this definition, and specifically the definition for an acid. An acid is a proton donor, so it gives up a proton. Is A or B my proton donor? And just for a moment, forget about any terms that I've used to describe that HCl. Is A donating a proton or is B donating a proton? A hydrogen ion. And what I want you to do is, before you answer that, look at your products. Yep, 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 yep. A. HCl is donating a proton. Fantastic. Great job. Now, with that knowledge, we're going to say that A is an acid. So, in any reaction where there's an acid, there is also a base. So, we would describe water as a base. Does everyone follow me there? Give me a Y or an N in the chat. B, water is a base because what did it do? It accepted a proton. A, HCl donated a proton. B was there to receive it. Okay, great. I'm seeing some good responses there. Now let's look at down at the bottom. Are there our other question? NH3 or H2O? Okay, we've got water again, and water is neutral. But where water is a little bit tricky is that water can act as an acid or a base. Now, using our definition, and let's go with just for the to avoid any sort of chaos here, C and D. NH3 or H2O. And then our products are NH4 plus and OH minus. Which one of these, C or D, is donating a proton? And look at the atoms. So we've got NH3, so that's a nitrogen. Then we've got oxygen, those are our central atoms. C is which one of them is donating a proton? How many protons or how many hydrogens does nitrogen have around it as a reactant, and how many does it have around it as a product? Well, as a reactant, it has 3 hydrogens. And then as a product over here, it's got 4 hydrogens. So did that donate or accept? If it donated, then it should have less. But as a product, it has more hydrogens. So what that means is that water, D, is donating a proton. And therefore C is accepting. Because we're going from this molecule to this molecule. Then we're going from this one to this one. So what does that mean in our second reaction there? How is water behaving? Is water an acid or a base? Give me a response in the chat. A for acid, B for base. Absolutely. Emma is absolutely spot on. Sophia, you're right as well. Michaelin, absolutely. Acid or water is acting as an acid. So in this case, it's an acid, and therefore this is a base. So if ever if ever you were asked the question, is water an acid or a base? This is one great example of why chemists and scientists um, they can kind of be tough to talk to from time to time because when you ask that question, you think to yourself, or I think to myself, straightforward yes or no question, binary questions, either this or this. And the response is, well, it depends on the circumstances. And is that wrong? No, it's not. Is there a general response? Yeah, water is neutral. Well, yeah, water, a singular water molecule, independent of everything else, is. But depending on what else is there, water might be acting as an acid, might be acting as a base. You just don't know, given the kind of generality of that question. Okay, can I get a Y and an N or an N in the chat? Y if you're good, and if you would like me to show another example. Okay. So now Lisa, I believe, was the first person to bring this up, and I don't know if anyone else has done so since, but Lisa asked about the pH scale. And good news, this is our pH scale. Our pH scale ranges from basically 0 to 14. Now, what this tells you is the relative acidity. So, how willing something is to give up a proton or accept a proton. And another way of looking at that is you could look at it in terms of how reactive something is with a metal. Over here on the acidic side, super reactive with metals, super reactive with lots of different things. As we learned from Breaking Bad, over here, super reactive with organic material, I'll say. Now, when you go from basically a low pH is aligned with a basic, or sorry, a low pH is aligned with an acidic solution. A high pH is aligned with a basic solution. A neutral pH of 7, that's smack dab in the middle. Now, what I want you guys to know about are extremes. HCl, sodium hydroxide, and then I want you to know that spot in the middle. Now, these things vary a little bit in terms of, well, their acidity, but I think that there's a little bit of a, um, these are, well, all of these things are examples of something that you've maybe had some exposure to in your lifetime. For example, if you've ever thrown up, oh, it feels gross. That's a super acidic solution. That's a gastric juices. That's a lot of hydrochloric acid, a lot of other stuff. Compare that to eating an orange or drinking a Coke. Well, are they both acidic? Yeah. Orange juice does. Oh, I hear you. Tomatoes are relatively acidic. Now, blood is a little bit basic. Things higher than that, seawater, baking soda. Well, if you were to go and get some baking soda and add it to water, you got like tap water and then added some baking soda is not going to go into solution, but if you took a drink of it, you're not going to, in fact, I'm not telling you to do this. I'm not saying, but that would be an instance if you made water with baking soda in it and you touched it, that would give you that kind of slippery feel to it that I was describing a little bit earlier. I know that there are some people, endurance athletes specifically, who will drink a glass or two of baking soda because they think that it helps them in their training. It helps them, oh, well, now I can run longer, or I can cycle longer, or whatever. Um, if you drank that, you're not going to throw up. Similarly, or yeah, you might not have that a violent response to it. But I want you to know this range. Low number, acidic. High number, basic. In the middle, neutral. I want you to be able to, if I gave you a question, and a good exam question for this would be something like, select the most acidic solution. And for that, I would give you examples. I would say, let's say coffee. I'm going to say hot coffee, cold coffee, and then let's go with milk. And I gave you a pH. Hot coffee, let's say that the pH equals 3.2. Cold coffee, pH 2.8. Milk pH, let's go with 8.1. I would want you to understand how to take this information and respond to a question like, select the most acidic solution or select the most acidic drink. In which case, I'd need you to know, oh, more acidic means lower pH. Therefore, my correct answer for this would be cold coffee. Absolutely. Cold coffee is more or most acidic because it has the lowest pH. Low pH, Lisa, low pH means more acidic or most acidic. Does that make sense? So hot coffee with a pH of 3.2, cold coffee with a pH of 2.8. 2.8 is lower, therefore it is more acidic. I'm just giving some hypothetical examples. These are not numbers that I know exactly. They're from cooking and baking, there are definitely some instances where cooking something does increase acidity. But I want you, sorry, I picked maybe a bad example. Let's go ahead and switch it from just so we can, for the record, let's go with cold coffee and let's go with Red Bull. If neutral isn't acidic or basic, is there a different word? Emily, it's just neutral. Um, and a good way to think about that also is however acidic a solution is, it's simultaneously that basic, so they cancel one another out. Or I hope that's a good way to think about it. But neutral is that's the technical term that anyone and everyone's going to use, both in like a healthcare environment as well as in a clinical or a laboratory setting. That's a really great question. Um, okay, so now Zoom poll. Let's see, we got that. No, not that one. A solution with a pH of 10 is A, acidic, B, basic, C, neutral, or D, toxic. That was my best singing along to the Britney Spears song Toxic. I'm going to leave this one up here for just a minute um, and tell you that there's one person in our class who joins the Zoom meetings at like 4 in the morning. I'm not sure why, but I get a notification whenever I'm not in a Zoom meeting if I have a room that someone has joined. And so I get notifications and I was like, that's strange. I think that they're probably joining so that they're there and they're ready. I hope that they're not like sitting for 5 hours waiting. Oh, when's he gonna show up? When is he gonna show up? It's gonna be about 9:30. Okay, so looks like the emerging answer is correct. Basic. The higher a pH, the more basic a solution is. So we got 65% of the class that came in with that. 66. I'm going to end the poll right there. So we got some other questions. I'll share the results and I'll also jump ahead to calculating the pH. Now, calculation of pH, it can be a little bit hairy because of the fact that whenever you calculate the pH of something, you are bringing a log in. You're bringing in logarithmic calculations. And Sometimes I know whenever I see log, I'm like, oh my gosh, I'm scared. Don't like. But let me tell you something. What we're going to do when it comes to a logarithmic calculation is we're going to keep pretty simple. Um, I'll show you this as an example. Let's see. For starters, pH is positive. So if we look ahead to the next question, we got a couple of different answers. We got one whole number, three whole number, -3 whole number but negative, and 0.001 number with a decimal position. Okay. Your pH is always going to be positive because it ranges from 0 to 14. So we can immediately strike answer option C. That leaves us with 1, 3, and 0.001. Now, before we get to that, we got to think about, well, hydrogen ion concentrations. Let's think about what this looks like kind of in a molecular sense. Let's say that we had two different solutions. One was HCl, and one was actually, I'm going to drop that from HCl. I'm going to say HX and H2Y. Okay, we got two different solutions here, or two different substances. HX. Now, if you add HX to water, this is X is like a place filler. It's a hypothetical molecule. If we add this to water, let's say that we've got 100 of these, 100 of each of them. When you add this to water, you end up with 50 that stay together as HX. And then you got 50 more that will split up. So if we think about HX as our compound, that will split into two different things. One of them is X minus, and then what's the other thing that it's going to split up to? What is HX going to split up to? X minus, and add to the chat what the other thing is. Close. It's going to split up into H plus. Because when you combine, it's going to, sorry, they're going to combine into HX. So we'll have 50 that stay together as one complete thing, and then 50 that will split up into H plus and 50 X minuses. Does everyone follow that? Now, when these things split up, this molecule, these 100 HXs split up, that means we're going to end up with, well, 50 hydrogen ions, 50 H pluses. And that right there, I'm going to erase the H2Y. We don't need that. That right there is what's going to give us information about the pH of our solution. Now, if we have a solution with a concentration where we've got, or no, sorry, just a second. What we're going to do with our pH, or to determine our pH, is we're going to take whatever the concentration is, the H plus ion concentration, that being 0.001 molar. So that means there's 0.001 moles in a liter of this. And all that we're going to do whenever you get this sort of question, we don't even have to do the calculation. You're going to be given hydrogen ion concentration. If you want to plug it into your calculator, go for it. But I'm going to save you the time. You plug that number in there right there. And a little bit of a spoiler is you basically just have to say, how many times does this decimal place move to give me a whole number? One, two, three. So the pH of a solution. A pH of a solution with a hydrogen ion concentration of 0.001, the pH is 3. You just count the number of places that that decimal moves. Now, with that, what is the pH? And I want you guys to add to the chat if a solution has a hydrogen ion concentration of 0.000 or sorry, 0.01. Add to the chat what's the pH of that solution? 4, because we moved our decimal 4 times. Now, I'm going to give you 2 different solutions, A and B. Hydrogen ion concentration, 0.01. Hydrogen ion concentration, 0.1. Which is more acidic, A or B? More acidic. Well, let's see. The pH of A is 2. pH of B is 1. So which one's more acidic? A or B? B. The lower our pH, the more acidic it is. So you see how this is like a multi-level sort of question. Okay. Now let's go ahead and proceed from here. This question, we'll go ahead and throw it into question. Let's see. Not that one. Launch this and then I'll go ahead and keep going. Okay. A solution with a pH with a hydrogen ion concentration of 0.001 molar has a pH of 1, 3. C is not an option. Please do not mark C, anybody. Or D, 0.001. We're moving our decimal. 1, 2, 3. Spoiler, it's not D either. Spoiler, the correct answer is B. Okay, so I'm going to go ahead and proceed from here. Litmus paper, this is exactly what it's going to look like in terms of acidity. Now, there's another type of litmus paper that's out there. It's not red or blue, but instead, this litmus paper is known as kind of a general acid base litmus paper. Or, sorry, there's another type of litmus paper where it just gives you an entire spectrum. Yeah, there we are. And this is kind of referred to as all-purpose litmus paper. So this will give you the information about a solution. Is that solution acidic or basic? And you'd use this color key. If it's red, it's acidic. If it's dark green or deep green, then it's going to be a basic solution. Now, another thing that's kind of done like a kitchen chemistry sort of situation, you can make a red cabbage solution, and that is going to be sensitive to pH. It will change color. So basically, what you're going to do is get red cabbage and kind of mash it up like you're going to make sauerkraut, get the water out of it, and well, you'll be able to add or you'll be able to change the solution color based on if you've added an acid or a base to it. And so we'll proceed from here. Now, With that in mind, what I want to talk about now, so this is available for you. This PhET simulation is available if you want to proceed and play around with that. That's not a requirement or anything like that, but I think it might be helpful to make like a basic or acidic solution. Now, what I want to talk about for the last little chunk of class is a strong acid versus a strong base. So, strong acids and strong bases. Here's those household solutions. And then here is a table of ions. Polyatomic ions, most common polyatomic ion that you guys need to keep in mind and that will really help you when it comes to acids and bases, which is hydroxide, the hydroxide ion. Anytime you see OH minus, think hydroxide. Now, you're going to be given this table on your exam, this polyatomic ions table, but of all the information that's on there, the most commonly used information is going to be the hydroxide ion, so OH minus. So if you know that, that's going to really help you out quite a bit. Now, acids are typically going to look like this, and bases are typically going to look like this. Acids usually have a hydrogen ion, HCl, and then acetic acid, H, C2H3O2. Um, Bases, they'll generally have an OH, but not always, as is the case with ammonia. Now, the reason for this is because this is a question of how they behave in a solution. HCl is a strong acid, so that will completely separate into a hydrogen ion and a chloride ion. The name that we use to come up with that, I think, and add to the chat, Y or an N. Have you heard hydrochloric acid before today's class? Have you heard that term, hydrochloric acid? Okay, great. What about sodium hydroxide, NaOH? Have you ever heard sodium hydroxide before? Okay, so these have kind of like worked their way into what's the word? The everyday language. You might not necessarily hear it every day, but it's maybe something that you have heard in your life. Now, by knowing it as hydrochloric acid, you've actually used the rules for naming an acid. The rules in the way that this is done is whenever you have something like this, chloride, Cl minus, that is the chloride ion we have right here. Chlorine, if you remember, is one of our diatomic elements, Cl2, chlorine gas. Now, chloride is an ion, and that is the form of chlorine where it's just floating around as itself or by itself. So what we do is we add hydro before it, and then we drop IDE and replace it with ic acid. So let me ask you this. Is HF? HF. Okay, so let's work through this name together. F by itself is fluoride. So how would we apply this same sort of nomenclature? Well, we'd have to add hydro, and then we make this hydroic acid all one term. So we just kind of insert fluor. We're dropping IDE and instead saying ic. So hydrofluoric acid is HF. Now, this ion right here, C2H3O2. I'm going to jump back to our polyatomic ions. C2H3O2 is acetate. Okay. Then what do? We drop ATE and make it ic acid. Acetic acid. Okay. Now, let's go ahead and do another one. Sulfate. Sulfate's a little bit tricky, and it's kind of a I don't know if I would say kind of an exception where we're adding a little bit of a wrinkle to it. Sulfate, we add a little bit of a wrinkle because we look at ATE and we drop that. We add URIC, acid. So anytime you see that ic acid, think, well, that is stemming from something over here, this polyatomic ions chart. Now, when we look at these, and just as an example, we've got H2SO4. That is, you would see this SO4 on that polyatomic ions chart. H2, we've got sulfuric acid. C is our correct answer there. Now, what I want to do right here is see. Okay. I want you to look at these different options right here and these different solutions. So let's start the far left. We have a neutral solution. Now, I'd like you to add to the chat Y or N responses to these questions. Let's look at our legend. We've got H plus, K plus, NO3, and OH minus. If we have a bunch of H plus, what does that tell us about our solution? If we had a solution that was just H plus, how would we classify that solution? Acidic, basic, neutral? If it was just H plus, add to the chat. If it was just H plus, we would describe it as acidic. So H plus is a good sign that you've got an acidic solution. Now, think about what's the opposite of H plus. OH minus. So this guy right down here. Now, with that information, add to the chat, if we had a solution that was just OH minus, how would we describe that? Acidic, basic, neutral? Basic. You're absolutely right. So if we have lots of OH, that's a basic solution. Okay. Can I get a Y or an N? Okay, I've got a good idea of what constitutes an acidic solution. And likewise, a basic solution. So just to give you a little depiction here, H plus, H plus, H plus. That's acidic. And then here's another solution, OH minus, OH minus. That's a basic solution. Okay, so those are our extremes. We've got our acidic solution, we've got our basic solution. Now, looking at these different solutions, I want to kind of make sense of all of these. If we look at solution number 1 on the far left, we've got H plus, H plus, H plus, H plus, H plus, H plus. Could anyone add to the chat how many H pluses are in there? Okay, we got 6 of them. All right. So if it was just H plus, it would be an acidic solution. Does that solution have nothing but H plus? No, it does not. We've got 6 H pluses. And then we've got, I'm going to switch colors here. Go green. 1, That's an OH minus. So we've got OH minus, OH minus, OH minus, OH minus, OH minus, OH minus. How many OH minuses do we have in there? 6. So is it fair to say that we have an equal number of acid kind of forming atoms or molecules or ions as basic? Yeah. This solution has 6 hydrogen ions and it's got 6 OH minus ions. So this is equal parts acidic and equal parts basic, which is how we arrive at this solution being neutral. Can I get a Y or an N in the chat if you follow that? So if we have the same number of acidic elements and basic elements, then we have a neutral solution. They cancel one another out. Now, if we go on to our next solution, solution number 2. And this is exactly the sort of question that you'll see on your exam, where you basically take an inventory of what's there. So the first thing that I want to do is I want to see what the lay of the land is. What do I have in here? I've got these things that look like toadstools from Super Mario Brothers. So we've got OH minus. Then we've got a plus, so I've got H pluses. So I've got components of an acid and a base, and then I've got purple people eaters. I got potassium ions. Man, what does that do? What does that do? Oh shoot. And this is something I remember whenever I took chemistry for the first time. I saw that and I just thought, crap. I don't know what to do with that. I just I just don't get it. Why? Huh? Who? Where? Now, let's jump back a couple slides. When we're talking about calculating the acidity of a solution, what do we look at? We look at hydrogen ions. Now, does anywhere on this slide reference potassium ions? No. Actually, does anywhere on this slide reference hydroxide ions? No, it doesn't. So when it comes to determining if something is acidic or basic, what is the only thing that you actually care about? Add it to the chat. The only thing that we actually care about when it comes to determining the concentration or determining the pH of a solution is effectively hydrogen ions. So, do we care about potassium ions? Nope. We kind of don't care that much about hydroxide ions. Do we need to think about it? A little bit, but the only things that we are going to be like laser focused on are hydrogen ions and hydroxide ions. And so we're going to, count these up. How many hydrogen ions in this solution? I'm going to say 1 because I only see 1. I'm going to scribble it out just so I can keep track of things. How many hydroxide ions? 1, 2, 3, 4, 5, 6, 7. 7. You know what? I see some potassium ions, but I'm not really going to care about that. So, how would you describe this solution when you look at the hydrogen ions and the hydroxide ions? Would you describe it as acidic or basic? And the question is, what do we have more of? Do we have more of hydrogen ions or hydroxide ions? So add to the chat, would you describe this as acidic or basic? More hydrogen ions means acidic. Emma, spot on. More hydroxide ions means basic. Does everyone follow that? Can everyone add a Y or an N to the chat? Okay. Okay, great. Great, 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 great. Now, our last solution. I mean, you guys can see where I scribbled. You can see that it says acidic. But let's rationalize that. What do we have? We've got one, two, three, four, five, six. Six positives, six hydrogen ions. So H plus, six. Hydroxide ions, one. The rest, well, it's nitrate ions, NO3. Dun, 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 dun. Simply by having more hydrogen ions than hydroxide ions, we've got a solution that's more acidic. Now, what's important, and actually, before I proceed, can I get a response? Do you follow how to use a model like this to determine if something is acidic, neutral, or basic? Just to classify it. If I were to put something like this on the exam, would you get that right? Okay. So be ready for a question like that. Now, to put this in a different context and to kind of elaborate on this, um, our numbers are not always going to be six. It's not always going to be like, well, there's five positives and four negatives. Here, what we have is, well, 1.0 times 10 to the negative seventh hydrogen ions and 1.0 times 10 to the negative seventh hydroxide ions. Um, how would you compare the number of hydrogen ions and hydroxide ions on this slide right here? What would you say about them? Are those numbers the same? Yeah. And since they're the same, that would be a neutral solution. What do you think would happen to the pH if this number on the left went way up? How does this impact pH? Is our pH going to go up or is it going to go down? When the number of hydrogen ions, number of more acidic, smaller pH. Emily, right there, spot on. That's it. That's what you need to know. As the number of hydrogen ions goes up, the pH gets smaller and the solution becomes more acidic. Now, when the number of hydrogen ions goes up, the number of hydroxide ions is going to go down. Those two things kind of work in complement one another. Okay. Now, acids and bases, what they can do is they can conduct electricity. Now, to illustrate that, this right here. We have examples of strong acids and strong bases. A strong acid will ionize completely in water. And what that means is that HCl, as an example of a strong acid, and then NaOH, as an example of a strong base. When it ionizes, what that means is, or another way of putting it, is it separates. HCl will separate into H plus and Cl minus. Could anyone add to the chat, what does NaOH separate into when it ionizes? Spoiler, it's going to go into two separate things. Perfect. Okay. Now, what that means is that if you have 100 molecules of HCl and you add it to water, you're going to end up with 100 hydrogen ions and 100 chloride ions. Sodium hydroxide, strong base. If you add that, if you have 100 molecules of that and you add it to water, you're going to get 100 sodium ions and 100 hydroxide ions. Can I get a, well, yeah, we'll just go from there. A weak acid and a weak base. I think that it's very tempting to hear strong acid, strong base versus a weak acid and a weak base, and think about it almost like one of them's more hazardous to a person than the other. Not necessarily. That definition of strength comes from it how much it will ionize. So a weak acid will only slightly ionize in water. So what that means is if we had a weak acid like HCN, that's an acid known as cyanic acid. What that will separate into is it will separate into ions. But the important part about this is that the numbers that it will separate into, H plus and Cn minus. Okay, so if you had 100 molecules of HCN and you added it to water, what would result is you'd get, let's say, 5 hydrogen ions. How many Cn minuses would you get? Well, we'd probably get about 5. Okay, so what does that mean? We had 100 of them. We added them. 5 of those molecules separated. What also happens is you got 95 HCN that don't separate. They remain intact. So now that's an example. That is kind of your definition for a weak acid. Now, if we had something like a weak base, Mg, actually, yeah, no, that's good. Um, MgOH2. Again, we've got 100 molecules of this. We're going to get, let's say, 8 Mg. How many OH will I get from this? How many free OH minuses? That would be 2 plus OH minus. Add to the chat how many OH minuses there are going to be resulting from this. And this is a little tricky of a question, or a little bit of a tricky question. We have to think about our ratios here. And then also add to the chat somebody, how many MgOH2 will remain intact? So we got 8 MGs that those are going to separate off. I'm going to have 92 of these, and these are just random numbers that I picked up. Okay, sorry about that, Maggie. That's what I was going for, though. We've got 92 MgOH2. Now, my question then is, how many OH minuses will you have? And just so you guys know, I'm going to draw a little bit of a model. We've got MgOH, OH. How many OH minuses will come from 8 MgOH2s splitting off? Or 8 Mg pluses, 2 pluses? And like I said, this is kind of a tricky question. If we get 8 Mg2 pluses, that means we've got 8 of this whole thing. that broke up. So then we're going to have 16 OH minuses. Can I get a Y or an N in the chat if you understand that? Okay. Okay, good. Good. So the point is, when it comes to a strong acid and a strong base, those will completely separate. A weak acid and a weak base only slightly separates. Now, here are the lists of your strong acids and your strong bases. There's 7 strong acids that you need to know. There's 6 strong bases that you need to know. I will ask you a question that is as explicit as which of the following is a strong acid? Which of the following is not a strong base or something like that? So I need you to commit these to memory. Now, one thing that's helpful to know these is if you look at HCl, HBr, HI, those are all in the same column on the periodic table, Cl, I, and Br. Um, then there's lots of different mnemonics. And the mnemonics that are the best are the ones that are the crudest, so I can't really share those. But my point is that I want you to know these because I will ask you a question, basically a memorization sort of question. These are strong. Everything else is a weak acid. So, as an example, which of the following, or sorry, classify HCN. HCN, simple question, or sorry, a process to go through is HCN. That's an acid. How do I know that's an acid? Well, because I see that H as opposed to OH. So I see H and I think it's an acid. So that gives me the power to cross these out. I've got acids, bases are out, and then I've got salt. Now, follow up CN, HCN. Is it a strong acid? No, it's not. So A is out. So I'm really left with weak acids and salts. Have we talked about salts? We have not. So at this point in class, B is our answer. It is a weak acid. Now, a chemical reaction where you mix an acid and a base is known as a neutralization reaction. Because what do you get out of it? H2O, a neutral solution. You have equal parts acid and equal parts base. You mix them up, you get water, and does it NaCl is our great example of table salt, and this is classified as a salt, the compound. Now, this is one of my favorite chemistry jokes. I'm going to skip it. Now, with that in mind, I want to work together through this and predict the products of these neutralization reactions. The first one, what's your product from H plus and OH minus? Add it to the chat. And while you're doing that, I'm going to go on to the next one. The next one, I'm going to use a simple sort of formula. AX plus BY. Your products of an AX plus BY reaction are AY plus BX. So whenever you see this, what you need to recognize are what is A and what is B, what is X, what is Y. Now, I'm guessing most of y'all have gotten this first question. H plus OH minus is H2O. Now, looking down below, this is a neutralization reaction. We are always going to get water, H2O, as one of our products. So I'm going to put H2O for both of these reactions. I can give myself a little bit of space so I can write any sort of coefficient before the H2O, but I know that H2O is going to be there. So what I'm going to do is I'm going to look at my reaction below, reactant, this one and this one. H and OH. That's effectively my AY. So what that means is the other thing is going to be my BX. Now, that means I'm going to combine Ca and Cl. The question, though, is do I need to worry about any sort of coefficients? I do. Why do I need to worry about a coefficient? Well, because I have to get the right ratio of reactants to one another. H is a plus 1, Cl is a minus 1. OH is a minus 1, and I've got two of them. That means that Ca is plus 2. Where else would I get that information? It's on the periodic table. So in order to get this compound right here to be balanced, it has to be CaCl2. Now, a fair question is this balanced? Okay, so let's go ahead and I'm going to erase some of my markings. And I'm going to look at calcium. Calcium's balanced. Cl2, I've got 2 on the product side. I've got 1 on the reactant side. I'm going to put a 2 out in front of that. So that means I've got 2 Cls, those are balanced. 2 hydrogens, 2 more hydrogens. That gets me up to 4 hydrogens. Okay, so now on my product side, I've got 2 hydrogens. If I throw a 2 out in front of that, now I've got 4 hydrogens. How many oxygens? 2 and 2. I'm balanced. Now my next reaction, same thing. I'm making water. And what I need to recognize is what are the other things that are not being used to make water? Na and SO4. So NaSO4. The question is SO4, NaSO4, is that balanced? It's not going to be. What is my charge on sodium? You'd see this on the periodic table and see that it is plus 1. What about SO4? Well, you could look at the polyatomic ions list. You could also look at this right here and see, well, hydrogen is plus, and I've got 2 of them. SO4, therefore, must be minus 2. So in order to get this balance, we've got to have Na2SO4. And if that's something that you're like, how am I supposed to remember all this? Well, we're going to be getting into this sort of deduction on Wednesday. So we'll be getting down to those numbers a little bit more, going into this a little bit more on Wednesday. Now, next up, though, is to balance the overall reaction. H2, SO4, Na, OH. First thing that I'm going after is I'm going to put a 2 out in front of the Na because now Na is balanced. So we're good there. SO4, well, that's balanced, so I don't need to worry about that. But what this 2 did here is it doubled my oxygens and it doubled my hydrogens. So I've got 2 hydrogens, I've got 2 more hydrogens, so I've got a total of 4 hydrogens, so I'm going to throw a 2 in front of that. I've got 4 hydrogens, 2 oxygens. I'm balanced. Okay, now this is going to be worthwhile for your activity, or one of your activities this week. Your quizzes are going to be posted a little bit later today, so anticipate those. I've got basically 2 more quick slides. This is kind of a repeat of the previous one, and just kind of a repeat or a good way to think about a neutralization reaction. When we react acid and base, strong acid, strong base, what salt is formed? Okay, good question. Is water a salt? No, it's not. So that's out. What is formed is a compound made up of Ba and Cl. Well, what's the charge on Ba? That's plus 2. How do we know that? Well, because OH is minus 1. So we've got 2 of those, so BaCl2 is our correct answer. Okay. And then that's pretty much it. With that said, thank you guys for coming to class. This was a lot of information, so please be patient with yourself. If you've got any questions about this stuff, let me know. Other than that, I hope you guys have a great Monday. Um, and I will see you on Wednesday morning, unless you drop by my office hours. I'd be glad to help out. Yes, I believe the activities are linked. Let me make absolutely certain, though, before I uh, this. Yes, they are. And I've gotten some folks, make sure that you convert everything to a PDF. If you have a JPEG, you got to throw it into a Word document or an Office document, export that or print that as a PDF. I got my email is joelgray@txstate.edu. Have a great Monday, everyone. Thank you guys for coming to class. Thank you very much. See y'all.